So we started our discussion with higher dimensional systems in the last class, and there one of the important thing that we discussed towards the end is that uh, we require to go to a non-Cartesian coordinate system. That means our p square. So since p square is always written as minus h bar square del square, then we require del square to be written in different coordinate systems. For example, in the last class we have seen in plane polar coordinate system, plane polar coordinates, that is given by r comma theta, where we have Cartesian coordinates written in terms of r and theta is y equal to x equal to r cos theta and y equal to r sin theta. So we had shown that del square in this thing is written as del square by del r square plus 1 over r into L by del r plus 1 over r square into del square by del theta square. Okay, then I left it for you to use this result and show that in spherical polar coordinates, namely r, theta and phi, okay, in spherical polar coordinates, we can write where of course here you know that x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. So this particular changes, this particular definition of spherical polar coordinates will give us a del square, which is equal to del by del r. So 1 over r square into del by del r into r square del by del r plus 1 over r square sin theta into del by del theta sin theta del by del theta plus 1 by r square sin square theta into del square by del phi square. So this is an expression for spherical polar coordinates. Now this is something which we should use in our applications, and I think it's not very difficult for you to guess what is del square in cylindrical coordinates. So I will not write it here. I will leave it for you to write it. Okay, so this is an easy exercise. Okay, so now let us try to understand. So let us try to do some simple problems using these things. So one of the simplest problem is that of a particle on a ring. Okay, of radius capital R. Let's see. Now this is something. So if you say that if you say that you have got a ring of radius capital R, and particle is allowed to only move on this ring. Okay. Um, then then you have, just 1 minute. Sorry. So so we have something like a particle on a ring. That means if you go back to this plane polar coordinates, this capital R, so R is equal to capital R, that is fixed, that is not going to change. So your wave function will depend only on theta. That means theta is the only variable. So for this, since so I'm looking at this one. So since theta is the only variable, theta is the only variable. Okay, one angle variable. So that means your wave function is only a function of theta. Okay, so that means we can write down the Schrodinger equation. It's a free particle on a ring. Okay, so if you want, you can add. It's a free particle on a ring. That means there is no potential. So that means your del square. So this means your del square has to be written as, you go back to this, since it doesn't depend on R, this term will not contribute anything, this term will not contribute anything, and small r is equal to capital R. So that is equal to 1 by R square into del square by del theta square. So this is your del square. So your eigenvalue equation, that is, we are always interested in this equation. So H psi is equal to E psi, where this H is P square by 2m, which is equal to minus H bar square by 2m into del square. But we have del square to be given by this. So this gives you that this is equal to minus H bar square by twice m r square into del square by del theta square. And we know that if m is the mass of the particle moving on the circle, and this mr square is basically the moment of inertia. So you can write this as minus h bar square by 2I into del square by del theta square. So this is a general feature that whenever an angular coordinate is sitting here, instead of mass, you will have the moment of inertia. Okay, so now let us try to write down this equation. What we have written here is just the Hamiltonian. So we can say that minus h bar square by twice I into, okay, this is just a one-dimensional problem. So d square psi of theta by d theta square is equal to E into psi of theta. So this is the equation of to be solved. That is the time independent Schrodinger equation or eigenvalue equation. Okay, so I can write this equation in this fashion: d square psi by d theta square plus twice IE by h bar square into psi is equal to 0. Okay, so I didn't write that here. I is the moment of inertia given by mr square. And now let us set let some k square be equal to twice IE by h bar square. Okay. Then this equation is d square psi by dx square plus k square psi is equal to 0. Okay. And remember, k square is positive. So that means
So d square psi by d theta square, sir.
d theta square. Yeah, thank you. So d square psi by d theta square plus k square psi is equal to 0, which means this will have an exponential, complex exponential solution or trigonometric solutions. Okay, so we could have written this psi of theta to be some a into e to the ikx plus b into e to the minus ikx, or we could have also written this as psi of theta is equal to some a prime cos kx plus b prime sin kx. Both are correct. I mean, both are correct. Both are solutions of this equation. Now, a prime and b prime and a and b can be related. This you know already, because e power ikx can be written as cos kx plus I sin kx. These coefficients are in general complex. So there will be some relation between a prime, b prime, and a and b. Now, when we try to do this problem of particle in one-dimensional box, we have chosen a cos kx plus b sin kx because that suited the implementation of the boundary conditions mathematically simpler. Now here we have to ask, what kind of boundary conditions should we implement for this? Here the boundary condition is that since this is a ring, okay, so psi of theta must satisfy the periodic boundary conditions. That means psi of theta plus 2 pi should be same as psi of theta. Psi of theta plus 2 pi should be same as psi of theta. Now, implementing a boundary condition like this is more easy in terms of an exponential. So, let us try to take one of the solutions. Okay, so let psi of theta be equal to some constant a into e to the power ikx, ik theta. Okay, I think I have been mixing this theta and x. Okay, so please, wherever I put x, uh, replace it with theta. Now, whatever happens to this one will happen to e to the minus ik theta also. So let us just look at this one. Then you have psi of theta plus 2 pi is equal to a e to the power ik into theta plus 2 pi. And this has to be equal to e to the power ik theta. That is the requirement of this boundary condition. Now this can be written as, okay, so this can be written as, it implies a e to the power ik theta multiplied by e power ik 2 pi is equal to e to the power ik theta. Okay, this also, there should be a here. So a e power ik theta. Now you can see a e power ik theta is here, a e power ik theta is here. This implies that e to the power ik 2 pi should be 1. Okay. Now you ask a question when this will be 1. So this implies your k has to be an integer. it has to be an integer. Any non-integer values, if you have, then e power I non-integer times 2 pi is not equal to 1. Only if it is integer, e power I 2 pi is 1, 2 pi is 1, minus I 2 pi is 1, etc. Okay, it should be an integer. That is, your m can be 0, or it can be plus minus 1, or it can be plus minus 2, etc. Okay, so this is what is that the quantization that we get. Now look at the way we have defined our k. From here we can get energy eigenvalues, because now we know what k is. So the energy, so energy values allowed are given by, let me write down E suffix m, because it depends on this m, is equal to h bar square m square divided by twice I. Okay, so these are energy eigenvalues. Okay, now our energy eigenfunction, so psi of theta is equal to some constant into e to the power I m theta. Now we have to get this a by normalization. Okay, so what is the normalization? Because the range is between 0 and 2 pi, we get a square integral 0 to 2 pi e to the minus im theta, that is the adjoint of this, into e to the im theta d theta has to be equal to 1. Okay, so this is what we talk about normalization condition. So e to the im theta and e to the minus im theta will become 1. So integral 0 to 2 pi d theta is 2 pi. So this gives you a square into 2 pi is equal to 1, or a is equal to 1 by square root of 2 pi. So we have solved this problem exactly. So the solution is we get all the energy eigenvalues and energies. Okay, so h psi m of theta is equal to E psi m of theta. Okay, or Em psi m of theta. Okay, so the solution of this equation, is given by Em is equal to h bar square m square divided by 2I, and psi m of theta is equal to 1 over square root of 2 pi into e to the power im phi. Okay, now you can see that okay, so this is the complete solution of this problem. Now let us try to make some remarks with respect to this problem. Okay, so some remarks. Okay, so the first remark is with respect to notation. So here m is a quantum number. Not mass. And we are not using mass here. So here mass is not used, but moment of inertia is used. Of course, it is related to mass, but we should not confuse by writing I as mr square and cancel this m and that m and get into some confusion. So this is one thing which I want you to keep in mind. So this remark is purely about the notation. And second one is that uh, EM is doubly degenerate. Doubly degenerate for all m except m is equal to 0. So m is equal to 0 is the ground state. M is equal to 0 is the ground state. Now, except ground state, all other excited states are doubly degenerate because your for m not equal to 0, we have 1 by square root of 2 pi into e to the power im phi. Sorry, why I am writing phi here? It's the theta. Okay, I'm sorry for these confusions. So e to the power im theta. I hope I wrote everywhere consistently. Okay, we have e to the power im theta and 1 by square root of 2 pi into e to the power minus im theta. Okay, we have these two functions that are eigenfunctions of the Hamiltonian with same eigenvalue. So that is why each of the em, that is m is not equal to 0, is doubly degenerate because there are two eigenfunctions corresponding to same eigenvalue. Okay, this you can call it as psi m of theta. Okay, so we call this one as, let's say, psi m of theta, and we call this one as psi minus m of theta. So both functions are having the same energy eigenvalue. Now, in addition, we can define, okay, so in addition, so this is just you notice that this one. So whenever you have degenerate eigenvalues, then we can say that so we can say we can write something called a phi of theta that is equal to 1 by root 2 into psi m of theta plus psi minus m of theta. Okay, so I will call this as phi m of theta. I can't call it phi m of theta. So let us simply call it as phi of theta. Okay, so note that phi of theta is also an eigenstate, In fact, I don't have to put 1 by root 2 here. I could simply put some C1 here and some C2 here, such that mod C1 square plus mod C2 square is equal to 1. So more generally, I can consider any linear combination with complex coefficients C1 and C2 satisfying this condition, normalization condition. Then such a construction is also an eigenstate of Hamiltonian with same eigenvalue Em. This you can verify. You apply the Hamiltonian on this function, and then you can see this. Okay, so this linear combination is also an eigenfunction of H with the same eigenvalue. Okay. Now I would like to make my third remark. So here we are going to define an operator which I will call it as LZ operator, because I am assuming that this ring is on the xy plane. That is why we wrote x equal to r cos theta, r sin theta, and the angular momentum around this ring, it will be Lz, because that is the z component of the angular momentum. So this can be defined as h bar by I into dou by dou theta. Okay, if I write like this, then I can write down this this Hamiltonian. Okay, so somewhere so I have written this Hamiltonian p square by 2m. So this p square by 2m, now I can write it because the only angular motion is there along this. So this I can write it as Lz square by 2i. Lz square by 2i. So now if you remember, this Lz is written in this fashion. Lz is written in this fashion. Lz square will be minus h bar square by del square del theta square. Then that equation will be similar to this. So I mean it is same. Hamiltonian is written as Lz square by 2 times the moment of inertia. Okay. Now what is the point that I'm trying to make here is that if your Lz operator is this, then suppose what is it if your Lz is operating on your psi m of theta, so that is equal to h bar by I into del by del theta operating on 1 over square root of 2 pi into e to the power im phi. Okay, so maybe let me put plus and minus here. Okay, plus minus here, so that I will get the results at one step. So that is equal to h bar by I into, I will get, I'm once again sorry, this is theta. So I will get plus minus Im, right? So I get plus minus Im out, and then this is 1 by root 2 pi e to the power plus minus Im theta. So this I will cancel with this. So you get, this is plus minus h bar m into psi plus minus m of theta. So you notice that e to the power im phi, im theta divided by root 2 pi is an eigenfunction of Lz with an eigenvalue h bar m e to the im theta by root 2 pi. Okay, and Lz e to the power minus im theta by root 2 pi is minus h bar m e to the minus im theta by root 2 pi. Okay, so these two functions are eigenfunctions of Lz also. Okay, so now if you look at uh, Hamiltonian, okay, so note that Hamiltonian is basically Lz square by 2I. Okay, so also note that the Hamiltonian and Lz actually commute with each other. Okay, so if they are commuting with each other, then um, you can they can have some functions which are common eigenfunctions of these two things. Okay, so one can look for common eigen states of Hamiltonian and Lz, and these are the common eigenstates. For example, this is a common eigenstate of both, because for example, and e to the im theta by root 2 pi, this set of functions m is equal to 0 plus minus 1 plus minus 2 etc. are such common eigenstates. Okay, they are such common eigenstates. That means if you are considering, okay, so please understand that when I write psi m, okay, when I write psi m, this is this function. So psi m of theta is this function. Okay, so now you can see that suppose you have m, okay, m value, and then your em, and then let us try to write down. So so this is what I'm writing here is eigenvalue of the Hamiltonian and eigenvalue of Lz. Okay, so if m is equal to 0, this is 0, and this is also 0. So m is equal to 1, this is h bar square by 2I, and this is h bar. And m is equal to minus 1, this is same, but this is minus h bar. Okay, and this is 2, it is 4h bar square by 2I, and it is 2h bar, and m is equal to minus 2, this is same, but this is minus 2h bar. Now if you go on doing this, you will see that for some arbitrary m, this is h bar square m square by 2I, and this is h bar m, and for minus m, this is same, and this is minus h bar m. Now if you look at this the set, okay, so you look at the set of these two values. That means this one, this set is 0 0, this is this set. So if you look at the set, these sets are different, no set is same. Okay, so so when you define um, eigenvalues of so let us say let em and let me define some lm are eigenvalues of I mean h and lz respectively. Then the set em comma Lm. Okay, if you take this set, they are distinct sets. They are distinct for each m. Okay, so that means um, these common eigenstates that we have, okay, are all orthogonal. Okay, so that means the psi m theta for or the psi m theta are orthogonal. So if you want to find out an orthogonal basis of the Hamiltonian, when there is a degeneracy, it is not sufficient to look for this one alone, but you have to look for example, uh, as we have seen here, this phi of theta, in this second remark, I made this phi of theta. So phi of theta, so note that phi of theta, which I defined as C1 times psi m of theta plus C2 times psi minus m theta, such that mod C1 square plus mod C2 square is equal to 1. Okay, so Hamiltonian operating on phi of theta is equal to same Em into phi of theta. So it's an eigenfunction of Hamiltonian. But Lz operating on phi of theta, which I will leave it for you to show, is not equal to some constant into phi of theta. So this implies phi of theta is not an eigenfunction. Not an eigenfunction of Lz operator, and therefore is not a common eigenfunction. Therefore is not a common eigenfunction of Hamiltonian and Lz. Okay, so in higher dimensional case, this is one feature which one has to be careful if you want to get an orthogonal, a correct orthonormal uh, set of eigenfunctions, then you should bring in a set of operators which commute among themselves. Okay, so
Excuse me, sir.
yes,
Sir, I have two questions basically.
yeah,
So, like here, when we found the wave function that psi m is equal to 1 by root 2 pi e power I m phi. So here, I think here we observe that it is independent of any physical variable of the ring. So I am just confused at how the information about system is carried to the wave function. Here I mean that like you find the probability of particle in if we want to find the probability of particle for the its position, then since it is independent of any physical variable of the system, then its probability will be always same, right? Whether the ring is of radius r or 2r, or the it is of a moment of inertia I or 2I. So how this information is being carried?
okay. So yeah, so that is okay. That question. Let me just come to that question, but let me see if I wanted to finish this part. Okay, so I just wanted to say one sentence here that the common eigenfunctions. So in general, uh, in higher dimension systems, in higher dimensions, in higher dimensional case, we Of course, this is not a higher dimension, but this is coming even in this case. So we have degeneracy in general in energy values, degeneracy for energy values, and in such case we need to work for common eigenfunctions of a usually a finite set of mutually commuting observables which are known by the name complete set of compatible observables. Complete set of compatible observables, which is generally shorthand written as CSCO. So here the Hamiltonian and then LZ is the CSC. Okay. Now I will try to, there was one lecture that I gave earlier on CSCO. I will try to share that lecture to you. It is better you go through that lecture, and next time when we meet, you can ask some questions wherever you didn't understand, because I think even if I do that lecture again, it may not come as good as it has come earlier. So it is better you take a look at that lecture and try to understand how the CSCO is important and how it comes, what is the mathematical origin of the CSCO. But later I will try to give you some more insight into the CSCO and degeneracy from the group theory and irreducible representation point of view, because we are also doing group theory. Okay. Now let us come to the question that you have asked. So let us call this remark number 4. Okay. So remark number 4. So our energy eigenfunctions are given by psi m of theta is equal to 1 by square root of 2 pi into e to the power I m theta. Okay. So now the question that you are asking, he is asking is that if you ask what is the probability, okay, so let's say probability that your the system is between theta 1, our system is an interval between theta 1 and theta 2. Okay, so that means we have a ring of radius r, and then let's say this is theta 1 and this is theta 2. Let's say what is the probability that the particle is there in this region? So that's a good question to ask. That is equal to integral theta 1 to theta 2 psi m of theta modulus square d theta. Correct? That is how it has to be written. So, but that's equal to 1 by 2 pi into integral theta 1 to theta 2. Mod square of this one is 1. So it is d theta. So that is equal to theta 2 minus theta 1 divided by 2 pi. So now the question that he is asking is that this probability is independent of any physical attribute of this particle. Okay, so this is basically this is uniform probability because it depends on the length, right? So when theta 2 equal to 2 pi, theta 1 equal to 0, the probability is 1, correct? So this is called a uniform probability. Okay, so now the question is that this is independent. Okay, so uniformity which is independent of moment of inertia, radius of the ring, and so on. Okay, yeah. So that is the question. But now the point that I am trying to make here is this is acceptable because any physics is not coming from the expression of probability, but it is coming from the eigenvalues and expectation values. Suppose I want to find out the average energy of the system. So average energy of the system. So average energy of the system is given by the Hamiltonian, which gives you the energy of m into psi m theta, and of course em into psi m theta and sum over m. Okay, if I have some arbitrary wave function, that is, let's say that, okay, maybe to be concrete, let's call phi of theta to be sum over m some cm into psi m theta. So this is a general wave function, okay, general state. Then my expectation value of Hamiltonian is going to be equal to sum over m em into modulus cm square. Okay, so the expectation value in this em, your physical quantities will be there, like this I or R, these things will be there in this energy eigenvalue. Similarly, you have a physical observable, all these physical quantities will appear in that one. It does not in general appear in the probability, correct? So that is the situation. So the probability of uh, finding the particle in this case is uniform. But if you have, for example, if you consider a case like this, okay, suppose you consider a wave function like this. Okay, so consider phi of theta, a equal probability amplitude construction of these two waves. So that will be something like some a into cos theta, let's say. Okay, phi of theta is a into cos theta, which is basically equal to some psi m of theta plus psi minus m of theta by root 2. So if you take something like this, okay, you can find out what a is. A has to be equal to um, okay, so root 2 pi. So I think it is 1 by root pi into cos theta. So I can figure this out. Okay. Now, suppose if you want to find out what is the probability for this, okay, so then phi of theta mod square is equal to 1 by pi cos square theta, correct? So that means depends on theta. In this case, your cos square theta probability depends on theta. So at different theta, the probability of finding the particle, if the wave function is like this, is different. But if your wave function is a common eigenfunction of both energy and the angular momentum, Lz, then that has this feature that the probability is uniform. Okay, so that's only a property of that wave function, but that does not that need not bother us, that that is independent of the physical probability. Here also everything is independent of physical quantities except that it depends on theta. Correct? Physical parameters enter into the description of expectation values through the eigenvalues of the operators.
Okay, sir, understood this. So I have another question. So like here, like when we were entering the negative sign for m, the corresponding Lz value, the eigenvalue for Lz operator used to negative and the energy is used to remain same. So does it mean that, is it because happening because momentum is a vector quantity and energy is scalar quantity?
Uh, yeah, in some sense, yes, because here the here plus m. Okay, so let's look at this one. So h bar m corresponds to a kind of a rotation in this direction, whereas minus h bar m corresponds to a rotation in this direction. So if you fix the energy, kinetic energy of the particle, it can have a kinetic energy in a positive direction or it can have a kinetic energy in the negative direction. So these two will have same energy. Okay, so these two will have same energy, h bar square m square by twice I. Okay, it is exactly like our particle in a box, one dimensional box. Also you may recall, you have 0 to L, then you have sine n pi by Lx is our solution, okay, root 2 by L. But now this is made up of two functions, right? So this is equal to root 2 by L into 1 over 2I into e to the power I n pi by Lx plus e to the power minus I n pi by Lx. So this is a wave function with plus p momentum, and this is a wave function with a minus p momentum. Okay, p equal to h cross n pi by L here, p is equal to minus h cross. That means there is one wave function which goes like this, and the other wave function which goes, I mean, the momentum. One wave function describes the particle moving in the positive direction, other wave function describes the particle in the negative direction. So it is equivalent to that.
Okay, sir. Thank you, sir.
Okay, so I will probably sign off from this, but then I wanted to just tell you that this kind of models are very important in chemistry, because people try to, for example, let's say that you have a benzene molecule. Okay, so you have this benzene, carbon, 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 and then there is hydrogen, hydrogen, hydrogen. So this benzene molecule is a hexagon, but then you can see that this benzene molecule is made up of some double bonds like this. Now these double bonds are kind of the electrons. When you have a double bond, one of the bond is called a sigma bond, the other bond is called a pi bond. Now electrons that are bound in a pi bond are very loosely bound. That means they are weakly interacting with the underlying nuclei. So if you consider these double bonds as weakly bound electrons, and those electrons can be considered in some approximation as free particles. Now these free particles actually can be there anywhere in this in this. So an electron that is free can actually be considered it as an electron on a hexagon. Okay, but then electron on a hexagon under another further approximation can be considered as an electron on a ring of some effective radius, which can be derived from this. So people try to make some models like this. Now I talked about benzene, but there can be other aromatic compounds in organic chemistry where the curvatures not hexagon or maybe more than there are more aromatic molecules which have more closer approximation to this ring. So this particle in a ring problem is very much used in chemistry to understand the spectroscopy of these organic molecules. So this is one application. Maybe if time permits, or I can at least share some references where you have this kind of applications. Okay, so and at this point of time, I also wanted to mention. I don't know if I mentioned this earlier. This particle in a 1D box of length L. This also has a molecule called 1,3 butadiene. I do not know if you people remember some organic chemistry from your BSc. So buta means there will be 4 carbon atoms. This is a linear molecule. Linear molecule. So we have 4 carbon atoms, and then diene means there are 2 double bonds and they are at 1 and 3 positions. So we have a double bond here and double bond here. This is the nomenclature. It's called IUPAC nomenclature, and this has a single bond. Now each carbon has 4 valence electrons, so there can be 2 hydrogen can bond here and only one here, and 2 here. So this is the chemical formula for 1,3-butadiene. Now the total length of this, you know what is the carbon-carbon double bond distance and carbon-carbon single bond distance. This whole thing is something like, I am just giving some rough numbers, 700 picometers. That is the length of this one. And now this is a pi, one sigma bond and one pi bond is there. This is one sigma bond and one pi bond is there. Each pi bond will have 2 electrons, one from uh, each carbon atom. So there are totally 4 electrons, and these 4 electrons are loosely bound. So this molecule can be now modeled. So model for this molecule is that you have uh, 4 uh, free and non-interacting. Each one of this is an approximation. 4 free and non-interacting electrons in a 1D box. So if you do this, then all our whatever we have done, particle in a one-dimensional box. Remember, the particle in a one-dimensional box, we had energy levels. En is equal to n square into h bar square pi square by twice ml square. So this is valid. This is completely relevant here. Now, since they are free electrons, there is no more change in these energy levels. And since they are non-interacting, they don't see that other electrons are present. So the only respect that we have to pay is to Pauli, because the electrons have to obey Pauli exclusion. So what you do is, let's say you have E1, and then you have E2, which is equal to 4 times E1, and then you have E3, which is equal to 9 times E1, etc. So you can say that the first ground state will occupy with 2 electrons. Pauli will not allow anything else. Then the first excited state will occupy 2 electrons. So the ground state energy, so ground state energy of 1,3-butadiene, 1,3-butadiene, of course in this model is 2 times E1 plus 2 times 4 E1. 2 times E1 plus 2 times 4 E1. So that is equal to 2 E1 plus 8 plus 2, 10 E1. 10 E1. Okay. Now, is there an experiment where we can choose what is the ground state energy? Maybe that is difficult. So, but how do we know whether this model is correct for this molecule or not? Okay, now you say that you supply some energy. Okay, so give some energy to the system. Okay, now what is the excitation that the system can takes place? So one excitation is that this fellow can go from here to here. That means the energy required for the excitation. Okay, so energy needed for excitation, is basically E3 minus E2 divided by, okay, this much is the energy required for the excitation. Okay, now how we are giving this energy, that depends on the experiment. Suppose let's say that we are giving this energy by means of light. Okay, so there is something called optical absorption. Let's say that we are doing this experiment, optical absorption. So what you do is that you go on giving electromagnetic radiation of varying frequencies. And now when the energy of your uh, radiation or the electromagnetic wave is equal to the energy required for excitation, the excitation takes place, so the energy from your electromagnetic beam will be absorbed. Otherwise, it will be simply transmitted. So now what you do is you do an optical absorption study. So you scan with a frequency here, and then let's say this is the transmitted uh, transmitted light. You measure the intensity of the transmitted light. Now you see that more or less it is going to be transmitted, and at some particular frequency you will see that there is going to be an absorption. Now this frequency is where, so you call this as nu star, and now you check so now you check if this nu star is equal to E3 minus E2 by H. Okay, so if this frequency is same as the frequency required, okay, so if yes, then your model is correct. If no, then the model is not correct. It turns out that in to a very good accuracy, optical absorption shows in this model shows that this model is correct for this molecule. Okay, so this is another example where chemistry people directly use the results of quantum mechanics in their laboratory. In fact, this 1,3-butadiene, I think at room temperature is a liquid. So one can do this optical absorption experiment by just taking that liquid into some small bottle and then putting in the optical absorption equipment, where the radiation of a different frequency is made to incident on that, and then whatever is transmitted intensity is measured. When the light is absorbed, you will have a dip in the transmitted intensity, and that frequency at which the light is absorbed is noted, and that is compared with E3 minus E1. You know here L is given, that 700 picometers, m is mass of the electron, and then other things are known to you, so you can calculate E3, E2, etc., and then try to see whether that nu is corresponding to this. And it turns out in this example, experiment showed that particle in a box model is a good model for this molecule. So this, I am sorry if this is a repetition, but I don't remember if I talked about this molecule when I did it earlier, particle in a box. But even if it is a repetition, it is worth mentioning it again. Okay, so this is, I think, our discussion with particle on a ring.
Sir,
Now, yeah.
sir, is the rigid rotator is equivalent to this particle in a ring?
No. That's a different problem. We will check what that rigid rotator is. But let us try to go step by
Okay,
step. So in the next problem, I'm going to, so I have used this one. If you remember, I used this formula. Now I want to use this formula completely before I go to rigid rotator. So now my second problem is particle on a circular disc. Okay, so next problem is particle on a, it's not a ring, but okay, I can call this a circular disc. It's a still two-dimensional problem, but it's not, I don't know DISK or DISC, but let us maybe
Sir, here it will, sir, I think here it will be dependent on both R and theta, right?
correct. So here it depends on both r and theta, and hence we have to use that full del square that I have for this. Okay, so here disk, let's say of radius r, okay, and it is a free particle. Particle, you can say, is confined to a circular disk of radius r. So a psi actually depends on both r comma theta. Okay, so now there are two boundary conditions. So boundary conditions. First boundary condition is that your psi,
Theta of,
yeah, theta plus 2 pi should be equal to psi of r comma
yeah.
theta. Okay, so for any r. So that is one condition. And the second condition is that psi of r equal to r and theta is equal to 0. That means there is, it is like there is infinite potential outside this. That is why it is said is confined. It's confined means there are infinite potentials infinite potential outside. So r equal to r psi of theta, that goes to 0. So these are the boundary conditions, and we of course must also say that we should not have any function that goes to infinity, because our wave functions have to be all normalized. Then you must say that psi of r at equal to 0 theta should be finite. Okay, so it should be finite. So these conditions are there, and then we are now ready. We can write down this Schrodinger equation. So h psi, as you see that as we go to more and more dimensions, introducing more variables, problems will become difficult, but there's something that are doable. So we can, but now our equation is minus h bar square.
Sir,
Yes.
your voice has become a little bit feeble, sir. Kindly keep your mic.
Yeah.
Sir, one more thing. In del square formula, I don't think we need to take the phi part of that. We will take only an r and theta part of it and neglect that
Yeah.
phi part of it.
Yeah. But as I was telling you, that I'm still with the two-dimensional del square. Okay, so I'm going to take this. Earlier, I have taken only this. Now I have to take this full part, right? So that way, I'm still with the two-dimensional del square, because this is just a circular disk or a circular plane.
Yeah, yes, sir. This is just like a special case of that particle in an infinite spherical well, like we are taking that azimuthal symmetry, I guess. That's
Yeah.
what.
So let's write that. So del square del r square plus 1 over r into del square, sorry, del by del r. plus 1 over r square into del square by del theta square. Okay, so maybe I should write psi outside, psi of r comma theta is equal to E psi of r comma theta. So this is the equation, and so let us try to pull out. So we are going to use our separation of variables technique, and we write down. And if you, I will skip a few steps, and I want you to fill those steps. I'm going to do a separation of variables, and then take this theta equation separately and r equation separately. And when I write down theta equation, I will exactly get what we have done earlier for particle in a ring. I know the wave function all that already. So I'm going to make use of the problem. So make use of problem of particle on a ring, and based on that, I'm going to write my solution, because this insight sometimes is very useful, is some function. Okay, so I will call that as let's say some f of r into e to the power im phi, im theta. So that is the solution, right? Okay, I can even put the normalization constant root 2 pi into im phi. Okay, this root 2 pi is not very important. That can be fixed finally also, but it is e to the power im phi. Now, if I substitute it in this equation, then what I will get is this theta differentiation is there only in this term, right? In all other places, you have only r differentiation. So we get minus h bar square by 2m, and that theta part will finally go away. So I have del square f of r by del r square plus 1 by r into del f by del r, plus I will have m square by r square, that is minus m square by r square, minus m square by r square into f is equal to E into f. That is what I will get. Because when I take double derivative of this e to the im phi, I get im into im, so I square m square, I square is minus 1, so I will have this this thing. Okay, so now this can be written in the following fashion. This is only a function of r, so I write d square f by dr square plus 1 over r into df by dr. I take this on the other side and then bring it here. So that will be plus twice m e by h bar square minus m square by r square into f is equal to 0. Now by an appropriate this one, so I can now at this moment say that if I choose a variable, okay, so maybe I put it like this. Okay, so I pull out okay, so I just wanted to bring it to some familiar form for you. Plus 1 by r into df by dr. Okay, so what I'm trying to do is I'm trying to say that I'm going to write r in terms of some dimensionless variable. So let us say I define some rho is equal to some k into r. Okay, define rho into some k into r. Then I have d by dr is equal to d by d rho into d rho by dr. But d rho by dr is simply k. So k into d by d rho. Okay, so then I will have here, so this equation in terms of this rho is k square into d square by d rho square into this f of rho plus 1 by, so r is equal to rho by k, right? So that is k by rho into another k, so that is k square into df rho by d rho. Then I will write this as twice me by h bar square. I pull out, then I get 1 minus m square divided by, I have to write down twice me by h bar square here also. So twice me by h bar square into k, rho by k. So that means it is rho square by k square is equal to 0. Now I have to fix the k. The k is something that requires to be fixed. Okay, so let us fix the k. Let us fix k by setting this factor equal to 1. By setting k is equal to twice, or k square is equal to twice me by h bar square. Okay, so if I fix that one, then what happens? This is basically k square. Okay, so this is k square, and this k square is there in this term, and in this term. So that can be pulled out, and right hand side is 0. So k square is not 0. So whatever is remaining is 0. So then this equation can be written as d square f of rho by d rho square plus 1 over rho into df of rho by d rho plus 1 minus m square by rho square into f of rho is equal to 0. So this equation, I do not know if you can recall or you are familiar. This is an equation whose solution,
Bessel function.
yes, it's a Bessel function. So this is a differential equation for Bessel function. That means we have f of rho, or f of rho is equal to some JL of rho. JL of rho. There will be a quantum number associated with this that we will call it as L, and we have JL of rho. Now you can see that your so we have a boundary condition. Okay, so what are the values of energy? The boundary condition tells you that your psi at capital R comma theta is equal to 0. This implies your JL of KR is equal to 0. That means the energy eigenvalues are the what is called the allowed values. Allowed values of K are can be obtained can be obtained from zeros of Bessel functions. Zeros of Bessel functions. That means the first zero, that is for a given L, for a given L, the first zero is, let us call that as K1 times R is equal to some first zero, or K1 is equal to that first zero, the value at first zero divided by R. K2 will be value at second zero divided by R. So the Bessel function will have some structure like this, right? So if you have X versus JL of X, so this will have some value like this. Depending on L is even or odd, let us say that it will have a value like this. So this is the first zero, this is the second zero, this is the third zero, fourth zero, like that. And you find out these zeros, and they will give you the allowed values of K for a given L. Now these things will be different for different these things. So you can say that the energy eigenvalues will depend on these first zeros. Okay, so this is how you get the energy eigenvalues, and these zeros of the Bessel function can be obtained from the tables or some mathematics tables. So when practically you require the values of these energies, you can get from them. So this is
So,
yes.
so from where you get L value, sir? L value.
No, L is see, L can be varied. No, L can be varied from 0 to infinity. So L actually depends on what is your
Position of the,
so you
I mean,
can see,
position of zero.
no, yeah. I mean, the position of 0 gives you the energy, right? So
Yes.
if you look at this, okay, so maybe I should. Mhm. Okay, I think it is. We should not call L here. We should call simply M only, because that that M only is what is there sitting in that equation, right? So this is Jm. See, what I'm saying is that a general equation, that is Bessel equation. Bessel equation is something like this: t square by dx square sum f of x plus 1 over x into df by dx plus 1 minus n square by x square into f is equal to 0. This is the Bessel differential equation. And the solution for this is Jn of x, correct? So whatever is sitting here, this integer, is what will be your that thing. So in our case, we have that integer to be this m, right?
Yeah, that's what I got confused. Yeah,
It
you
is
put L now, sir. Yeah. Now this makes sense.
yeah, it is Jm of x. And so for a given m, we have to say, for a given m, the first zero is like this. Okay, so this is the quantum mechanics of particle on a disk. Okay, and so you can see that the Bessel function is what is important, and the Bessel function is, if you have not studied Bessel function in your special functions, then I think you may have to little bit recall. Recall means what? If you want to solve problems of this type, then you have to have some idea of what Bessel function is. Okay, so now I think we have done two problems corresponding to. So now there is nothing more that I can do with respect to this with respect to this del square, because I have completed two problems in a plane polar coordinates. Okay.
So now I have one doubt, sir. Sir, here can we solve like a 2D problem like this on separately a 1D problem and multiply the solutions so as to get a 3D problem? Because we use this partial differential equations, like the solutions are the solution of a given thing is multiplied, right? That's why we write the final solution. So can we look for a 3D solution like as I said, or we have to go specifically in spherical polar coordinates and solve it?
Yeah, so the point is that you can do that, but one has to be very careful because if you look at the way that we have done in this 2D, our r and theta can now be considered as r sine theta and phi in that case, right? And then
Yes.
you have other variable which also depends on r and theta. So I think you will not really gain any simplicity by actually doing this, because you have to actually calculate r sine theta and phi and r cos theta and other coordinates. So I think it is same difficulty will be there. So that is why you don't see, like the way I have tried deriving this del square in 3 dimension. I actually did that, right? I used only 2 dimension 2 times.
Yeah, so I applied the same logic here.
uh,
So I got that idea from there.
yeah, but I think if you do like that here for these things, um, I don't remember, maybe I tried it, I did not get much of a gain in terms of mathematics for that. Okay, so now let us look at the problem which I think Arup Jyoti was talking about. So this is the problem of a rigid rotator. Okay, so this is the problem of rigid rotator. Again, in spectroscopy, this is a very important problem because the eigenvalues of rigid rotator are used as the eigenvalues are used to determine the rotational frequencies for the rotational spectrum, microwave spectroscopy. So the rigid rotator essentially is that you have so in classical mechanics also you might have studied that if you have a particle m1 and another particle m2 and this is fixed, this L is fixed, okay, that is why this is called rigid. Okay, so now this problem can be translated into a one body problem. So let's say this is mass m1 and this is mass m2. An equivalent one body problem will have some point and then some mass, and this mass is the reduced mass. So that is equal to
M1 M2 by M1 plus M2.
plus m2. Okay, so this is something which always can be done. A two body problem can always be considered as a one body problem. Now this r is fixed. Okay, so this is fixed r. And then this particle can move anywhere on the surface of a sphere because the rotation can be there anywhere. So the degrees of freedom, freedom for mu are theta comma phi, because it can be moved on the surface of a sphere. So this rigid rotator is actually the problem we can state in the language that we have been doing is like a particle on the surface of a sphere. Sphere of radius r. So this problem and this problem are same, because rigid rotator is basically of two masses, and two mass problem can be converted into a single mass problem by using this reduced mass. And once you say that it is like this, 1 degrees of freedom of theta and phi, the particle is always confined. Okay, so particle confined to the surface of a sphere of radius r. These two are same problems. Now for this, we go back to our del square in spherical polar coordinates. Okay, so we go back to our del square in spherical polar coordinates. Now psi depends only on theta and phi. So that means this derivative does not play any role because it is small r is equal to capital R. R is fixed. So this derivative does not play any role. So your del square operator is going to be equal to, so del square, so remember here psi depends only on theta comma phi, and r is equal to capital R for all times. Okay, for all, this is fixed. So your del square operator will now be written as 1 by r square sine theta dou by dou theta of sine theta dou by dou theta plus 1 by r square sine square theta into dou square by dou phi square. So that will be our del square. Okay. Now you can say that this one, there are two things that we would like to do here. So we can approach from physical point of view. Okay, so let us go to classical physics. Okay, so many of these things I request you to try. In classical physics, we know that the angular momentum is defined as r cross. So you can write down what is your Lx. Lx is equal to, you know, that y pz minus z py, and Ly is equal to z px minus x pz, and Lz is equal to x py minus y px. So you know these are all operators. Now you know that your p, the operator p, can be written as minus or h cross by I into the operator del. So that is in terms of del by del x, del by del y, del by del z, and you write them in terms of the spherical polar coordinates and write an expression for, so write expressions for Lx operator, Ly operator, and Lz operator in terms of dou by dou theta and dou by dou phi. In terms of dou by dou theta and dou by dou phi, of course r is fixed. Then you can define an operator called L square, which is equal to Lx square plus Ly square plus Lz square. Okay, and show that the operator L square is equal to minus h bar square into 1 by sine theta dou by dou theta sine theta dou by dou theta plus 1 by sine square theta dou square by dou phi square. So you can see that this you can show. I am not going to do this. This is done in many textbooks, so please have a look at that one. Only algebra and some bookkeeping is required, so you can show this. Now, whatever I have written here, this del square operator with this particular case is simply L square by R square. Okay, so notice that this is L square operator by R square. Okay, so now the Hamiltonian, since it is a free particle, the Hamiltonian is equal to minus h bar square by twice mu, the reduced mass, into del square, which is equal to, I can write this as L square by twice mu R square. And twice mu R square is basically your um, moment of inertia, twice I. So just like p square by 2m, for a rigid rotator, the Hamiltonian is simply L square by 2i. Remember, in the ring case, we have only one of the components. L square is Lx square plus Ly square plus Lz square in general. And in a ring case, there is only one Lz component. So that is why we wrote it as Lz square by 2i. So the rigid rotator Hamiltonian is simply generalization of that. It is L square by 2i. Now we would like to find out energy eigenvalues of this L square. Okay, so that is what is important. So now the point is that this particular equation, okay, so like what we have written here, okay, so now I want to find out some function of theta and phi, right? So h bar square by 2i. So I get this, so the h psi is equal to e psi. H psi as a function of theta comma phi is equal to e as a function of theta comma phi, implies minus h bar square by 2i into 1 by sine theta. I don't have r square. R square is in this I now. Okay, 1 by sine theta dou by dou theta of sine theta dou by dou theta plus 1 by sine square theta into dou square by dou phi square into psi of theta comma phi is equal to e psi of theta comma phi. Okay, so now let me just do this separation of variables, at least in this case, so that you have seen it once. So theta of phi, I can call this as P of theta and Q of phi. So I can multiply this. So I will have 1 by sine theta, or I multiply this entire thing with sine square theta. So I get sine theta dou by dou theta into sine theta dou p by dou theta. Thus p is the function that depends on this, into q. Q of phi, I will write it outside. Q of phi plus p of theta into dou square q of phi by dou phi square is equal to minus twice IE by h bar square into p of theta to q of phi. Okay, so now divide this one with divide P of theta and Q of phi. Okay, so then I will have sine theta divided by P of theta into rho by dou theta into sine theta dou P of theta by dou theta plus 1 by Q of phi into dou square Q of phi by dou phi square. I could have simply written this plus twice IE by h bar square. So this is a function of phi, and then rest is only a function of theta. Let's assume like that. Then that should be equal. That should be equated to this entire thing. So what I should say, this entire thing is like you say this is plus m square and this is minus m square. Okay, so then m square minus m square will be equal to 0. So we will have two differential equations, that is d square q by d phi square plus m square into q is equal to 0. This is one equation. And the other equation is sine theta by P of theta into dou by dou theta of sine theta dou P of theta by dou theta plus we have twice IE by h bar square plus m sorry, this is equal to m square, so minus m square is equal. So this is another equation. Now this equation is basically the what we have is basically like particle in a ring. So this equation I can immediately write down. The solution Q phi is equal to same boundary condition it has to satisfy. So I will have Q phi is equal to 1 by root 2 pi into e to the power Im phi. So here I should write Im phi. Remember, so this is the solution for the phi part of this equation. Now the theta part of this equation is, so I can write this, so let us write this as, so let me write dou by dou theta of sine theta dou P of theta by dou theta plus twice IE by h bar square minus m square, so this quantity divided by sine theta is equal to 0. Okay, I think I have made a small mistake. So here, when I multiply this with sine theta, I have to also multiply the right hand side with sine theta. Correct? So there will be a sine theta component sitting here. So then in that case, this becomes simply m square by sine theta. Okay. So yeah. So now this can be written as let's say sine theta into d square p by d theta square plus cos theta into dp by d theta plus I have twice IE by h bar square minus m square by sine theta is equal to 0. Okay. Now let us say that we want to understand how this equation, or what this equation looks like. So for that, let us try to write down this in terms of some x is equal to cos theta. If I take x is equal to cos theta, then I will have d by d theta to be equal to d by dx into dx by d theta. Dx by d theta is minus sine theta into d by dx, correct? So cos theta differentiation is minus sine theta. Okay, so that is this part. Then, so that is equal to, suppose if I substitute that, then I'll have sine theta into d by d theta of another d by d theta, that is minus sine theta into d by d theta, sorry, d by dx, acting on some p of x. But of course, I have to write everything in terms of x, correct? So, okay, maybe let us just try to take this term. That is, I am going to take this first term and then write that as sine theta into 1 d by d theta is written as minus sine theta. I'm sorry, I am trying to do it partially. So this is minus sine theta d by dx in acting on p of x. But you know, since cos theta, x is equal to cos theta, your sine theta is basically square root of 1 minus x square. Okay, so if I have to write everything, this is minus sine square theta. So that is minus 1 minus x square, or that is x square minus 1 into d by dx acting on a minus sign. So I can pull that out and put this plus square root of 1 minus x square into d by dx. So which I can write it as 1 minus x square into square root of 1 minus x square into d square by dx square, plus I have to do a differentiation with respect to this, that is 1 minus x square into 1 by 2 root 1 minus x square into minus 2x into d by dx. Okay, so this root minus x square will be a root here, and 2 will go away, 2 will go away. So minus x into root 1 minus x square. And the next one is, so now let's look at this term. Okay, so let's look at this term. That is cos theta. Cos theta is x. Okay, let's write that. Cos theta into dp by d theta. That is equal to x into root 1 minus x square into d by dx of p of x. Because that is sin theta with a negative sign. Minus x into root 1 minus x square. And okay, so here, of course, I have to put sin theta here is equal to root 1 minus x square. That's the so how will the change? How will this equation look like? So the differential equation for theta in terms of x is equal to cos theta. So first thing we have is yeah, so 1 minus x square into root 1 minus x square d square by dx square minus x into root 1 minus x square d by dx plus twice IE by h bar square minus m divided by root 1 minus x square is equal to 0. Okay. So there is a P everywhere. So we have so let me see if there is any mistake.
I think this simplifies to Legendre function, right?
Yeah. So basically, I think we have to. So here you have to make one. See this particular equation. Okay. So I think maybe there is some term somewhere I made a mistake, or maybe there is no mistake. But what I'm trying to say is that this particular term, you must consider it as L into L plus 1 for some integer L. For some integer L. If you do that, then this equation becomes a differential equation for, that is, with this choice. Okay, so with this choice, differential equation for associated Legendre functions. Associated Legendre functions. Associated Legendre functions, which are written in this following fashion: PLM of x. Remember, x is cos theta. PLM of x. And if m is equal to 0, then they are called Legendre polynomials. Okay, these are not polynomials, these are called associated Legendre functions. But if m is equal to 0, then we have PL of x. And these are Legendre polynomials. Okay, and uh, we will do this in more detail in the next class. But I wanted to tell you that the complete solution, this psi of theta comma phi, okay, will be a function of this and this. So this is what is called a spherical harmonics. Okay, the eigenfunctions of the rigid rotator or the particle on a spherical surface is basically spherical harmonics. Okay, which is a product of associated Legendre functions into e to the power im phi. Okay, so this is called spherical harmonics. Okay, so you must have seen that the spherical harmonics can be written in terms of ylm of theta phi. Okay, this is very, very important because it comes in electrodynamics, it comes in many, many spherically symmetric problems. Okay, so this is given by square root of 2L plus 1 by 4 pi into L minus mod m factorial divided by L plus mod m factorial. This is your constant that comes in between, and PLM of cos theta into e to the power im phi. Now the interesting thing is all these prefactors we have to put such that when you do an integration over your solid angle d omega, your ylm theta phi or yl star of, these are complex functions, so ylm theta phi. So if you take some L prime and M prime here and LM here, then you have this L prime and M prime. They are orthogonal and also normalized. Okay, so this integral d omega is over sin theta d theta and d phi from 0 to 2 pi to 0 to pi, that usual integration. So the spherical harmonics are the most important functions, which are eigenfunctions of this theta phi. Now this is more important than in this problem because one of the big class of problems that we are interested in is called spherical symmetry, spherical force problems. That means problems in which your potential depends only on R. Now, when you have a spherical symmetry, that means when you have a problems in which central force problems are there, whatever is your potential, the potential is depending only on R, and only radial part of the differential equation will be different. The angular part is always like what we have just seen. So that means every central force problem, 2/3 of the problem is this problem, and the solutions are spherical harmonics. Only the radial function will be different. If you have a free particle, then you will have spherical Bessel functions. If you have a hydrogen atom, then you have associated Legare functions. If you have some other potentials, maybe you will have some other hypergeometric functions, etc. But the angular part of the wave function is always spherical harmonics, and hence it is important to appreciate these functions. So we will continue in the next class, maybe spend a little time on understanding the spherical functions, spherical harmonics, and then look at this problem of rigid rotator or a particle on a sphere, and then relax the conditions where we bring in radial coordinate. And then eventually, as I told you, our aim is to go to the solution of the hydrogen atom. So I am doing this step by step so that we understand the nuances of every problem and then see its relevance in solving the next problem. Okay, so I will stop here. You can ask if you have a question.
Sir, is the spherical harmonics comes only in spherically symmetric potential?
Spherical harmonics is a solution of theta phi differential equation in all problems where the potential depends only on R, that is spherically symmetric potential.
Oh, yes, sir.
Suppose if your potential depends on theta and phi, then it will not be same.
Okay, sir.